Now we're going to turn our attention to something that I'm sure you're all familiar with, ground fault circuit interrupters. Now, these devices are not the same as ground fault protection. I even see engineers screw this up on drawings from time to time. They'll say they want a GFCI when in fact they want ground fault protection. A GFCI is about people protection, whereas the ground fault protection scheme was about equipment protection, about fire protection from those high energy arcing faults. But this device is about shock protection for people. Essentially, what this device does is it monitors how much current is going out on the hot conductor and how much current is coming back on the identified conductor. If it senses a difference of 5 milliamps, as in 5 milliamps of current is not coming back, then this device opens up. So why 5 milliamps? Well, essentially, 5 milliamps is what we call the shock threshold. When you look at your body, consider your body as being a load or a resistor. When you apply voltage to that, the amount of current flowing through your body is inversely proportional to resistance and directly proportional to voltage. So, this goes back to Ohm's law. Current equals voltage divided by resistance. 5 milliamps directly to the human heart is enough to put the heart into fibrillation. So the GFCI is opening at that low threshold. Some of you are probably thinking, well, I've received a shock off of a 120 volt circuit and my heart didn't go into fibrillation. Well, that's true because in all likelihood your skin was intact. Your skin is a very good resistor and it does slow current down. On average, somebody receiving a shock from a 120 volt circuit with dry skin that's intact probably has somewhere in the neighborhood of 1 to 2 milliamps of current flowing through their body, which is not going to send your heart into fibrillation. But think about where we install these devices. We install them in places like around sinks or outdoors and on construction sites. These are all code requirements. These are places where your skin's resistance could be compromised because of damp or wet conditions. And also think about the other people who are using these electrical systems. It's not just you, it's your family, it's your friends. People who are older, their skin gets thinner as they age, and that reduces the body's overall resistance. The very young as well. Children, babies, they have not only thinner skin, but also smaller body mass, so they end up being more susceptible to shock injury. So these devices are protecting people, yes, at a pretty safe threshold, but for the very young and the very old, their overall resilience, body resistance, and body composition is going to be different than those of you who are in what we call the most survivable age, between the ages of 18 and about 35. And the devices are going to provide shock protection for those people. Next, we're going to talk about ground fault detection or ground fault indication. Manufacturers, suppliers, they bounce back and forth between these terms. The code does in fact refer to it as ground fault detection. And you're going to find this in Rule 10-400. This type of system is required for what we call an ungrounded system. That means that the transformer itself is not grounded. It's not connected to the mass of the earth. Therefore, it doesn't have the same stable voltages that you see with a grounded system. If you have unbalanced loads on an ungrounded system, you get a lot of problems with floating voltages. But the advantage of this system is that it can continue to operate under a fault condition. Now, just because it's an ungrounded system does not mean that we still don't have grounding. We still have a grounding electrode, and we still have what we call equipotential bonding. That's the bonding that connects all the non-current carrying metal back to the mass of the earth to make sure that the conduits, the enclosures, the outsides of boxes and panels and transformers and all that sort of stuff are not only at the same potential as each other, but also at the same potential as the mass of the earth. Under normal conditions, when you have a fault on this type of systems, maybe somebody pinches a wire underneath the connection box for a motor or something like that, you don't develop an arcing fault because there's no path for fault current to flow back to the source. You do have a fault. There's a short path to ground, but we've already established that Earth is just a big-ass resistor. There's no path for that current to find its way back to the transformer it came from. For all intents and purposes, you may as well be holding that conductor out in the air, because there's no place for current to flow. And that's the advantage of these systems, is just because you have a fault does not mean that you have to shut down. There's no fire or shock hazard. The only way somebody could get shocked by this is if they were touching bonded metal and another energized phase at the same time. Well, that's a dumb idea under the best of circumstances, so we're not too concerned about that. Therefore, the system can continue to operate under a single fault until the next scheduled shutdown. But we do need to know the fault exists. This is where ground fault indication comes into play. It's a way of showing that there's a fault so that maintenance staff who monitor the system regularly can identify that there's a fault and go find it on the next scheduled shutdown. Under normal conditions, you're going to find that all three of these lights are dimly lit. If we think about the theory here, each one of these lights is a fairly high resistance load. It's a tiny wire tapped off of the main conductors, and there is a path for current to flow through these lights from one phase to the next through the bond that they're connected to on the other end of those leads. So under normal conditions, you find all three lights dimly lit. However, if we introduce a fault into the system, somebody pinches that wire underneath the motor connection box, now current has a choice. It can go through that highly resistive load and teeny tiny wire to get back to the bond path, or it can take the big ass conductor straight there. Ohm's law says it's going to take the path of least resistance. So what we find under a fault condition is that the faulted phase light goes out and the other lights end up getting brighter. Now, what do you think the pattern would look like if we ignored that first fault, just kept running, or maybe we couldn't find it, because these things can be a pain in the butt to try to find, and over time a second fault develops. Maybe a wire insulation wears down in another location. What's the light pattern going to look like then? Well, I know some of you are saying, well, won't two lights go out then? If that was a C of Q chess question, you just screwed up and got it wrong, because we got to go back to theory. If a second fault develops, it's essentially like having a line-to-line short through the bonding conductor. And when you have a line-to-line short, the overcurrent device opens up. Or hopefully it does.